Welcome friends to Physics in 20 minutes. In the last few videos, we were developing the mathematical construct needed for this course. In today's video, we are going to start with our physics topic, and that is motion. In this video, we are going to learn about displacement, average and instantaneous velocity, speed, position time graph, and displacement from velocity time graph. You need to see the video number 13, 14, 15, which are a prerequisite as we are going to use a lot of calculus, that is derivative and integration, for this video. So what is motion? A lot of things around us do move. For example, in this picture, a highway has been shown. Cars and vehicles move on the highway. Although those distant mountains, they do look stationary. But as the earth rotates on its axis and it moves around the sun in its orbit, these mountains and all other large objects on earth which seem stationary, they move along with the earth. The earth moves around the sun itself moves in our galaxy, and all the galaxies move away from each other. So the world and everything in it moves. So motion is a very important part of our life. The kinematics, which we are starting with now, is a branch of physics which deals with types of motions and its classification without knowing the actual reason for the motion. In this and in the next few videos, we are going to discuss the simplest form of motion, that is motion along a straight line. We are going to consider motion of particle or objects which move like particles. In order to describe motion, we generally define a frame of reference. What is a frame of reference? A frame of reference is a set of coordinates predefined in order to study the motion of the body. What do we mean by defining a set of coordinates? So when you define a frame of reference, you actually define your origin and your axis, x, y and z axis. So for example, if you have a motion in one dimension, that is along a straight line, only one axis is sufficient to describe the motion. An example, let's see a car moves along a straight road. Then the direction of the road can be taken as x-axis. A suitable origin can be chosen. If the motion is along two dimensions, then you generally require two axes to define the motion. For example, if I have a carom board coin which is moving on the board, then its position can be described only by using two axes. If it's a three-dimensional motion, then you need all the three axes to describe the motion, that is x, y and z axis. Example, if the particle is moving on the surface of a sphere, then you require all the three axes to describe its motion. So how do we define position of a particle in one dimension? So since it is one dimension, that one dimension can be chosen as x-axis along which the motion is happening. As we have seen, we generally choose our origin first. Then we define our positive side of the x-axis and the negative side of the x-axis. In most of the cases, generally this choice depends on the problem at hand. Each problem is a specific and you have a choice to take the positive and negative side of the axis depending on the problem. So for example, here I can choose the right side as positive direction and left side as negative direction. Further, I can mark the coordinates in the units of distance like kilometer, meter or centimeter. In this setup, if a particle is on the left side of the origin, then its coordinate will describe its position and it will be negative position. If a particle is on the right side of the origin, it will be positive. So let us revise the important steps once again. First, you draw x-axis. Second, you choose the origin. Third, you mark the coordinates in the unit of length. And fourth, the position of the particle in one dimension is given by the value of its x coordinate. After you have described the positions, you can now go for displacement. So let's say along the x-axis, a car is at the position x1 at some moment. After some time, the car moves to position x2. How much would it be its displacement? Now, its displacement is generally defined as its final position minus initial position. That is x2 minus x1. This is generally represented by delta x. Here, delta x does not mean delta into x. Delta x means a small change in x. Capital delta is a Greek alphabet. So, the displacement delta x is given as x2 minus x1. Positive delta x means the motion is in the positive direction. Negative delta x means the motion is in the negative direction. So do remember the important points. The displacement is a vector quantity. Its magnitude is the shortest distance between the initial and final point. Its direction is from initial position to the final position. For a straight line motion, there are only two options. One is the forward direction and one is the reverse direction. So it can be shown using plus minus sign, provided you define the positive direction first. Then the opposite will be the negative direction. And its SI unit is meter. Going further, let's take an exercise to understand the concept that we have developed so far. A car is traveling on a straight road. It was initially at 30 meters from the observer. Calculate its displacement from the observer in each of the following cases. Also calculate the net displacement in each case. It went ahead to 100 meters from the observer. It reversed to 70 meter mark. It reversed to 10 meter mark. It's a rather simple problem. If you want to solve it on your own, please try to do that and come back and check the solution. Here goes the solution. Let us draw a rough diagram to understand the situation. I have my x-axis and origin marked. The car is initially at a 30 meter mark. From here the car moves to 100 meter mark, and then from 100 meter mark it reverses back to 70 meter mark, and then from 70 meter mark it further reverses back to 10 meter mark. So in order to solve this, we can draw a table. In the first column, we will calculate the displacement in each segment of the motion. In the second column, we will calculate the net displacement, both in meters. So in the first segment, final position is 100, initial position is 30, displacement is plus 70. That is towards the right side in the diagram. In the second segment, the car reverses back to 70 meter mark. So in this segment, its final position is 70, initial position is 100. So the displacement is 70 minus 100, that is minus 30. Negative sign here shows that the motion is in the negative direction. It was originally at a 30 meter mark, now it is at 70 meter mark. So it is 70 minus 30 and it is 40, and you can see that this displacement is still positive, that is towards the right side from the initial position. Third segment of the motion, its final position is 10, initial position is 70. So final minus initial, that is 10 minus 70 will give you minus 60. So displacement in this segment is minus 60 meter. Minus sign shows that the car has shifted towards left. What will be its net displacement? So you can see its initial position was 30, the final position is 10. So 10 minus 30 is minus 20. The net displacement is also negative. That shows the car has gone towards left from the original position. We have learned how to handle position and displacement. Now we will learn how to calculate velocity in one dimension. First, starting with average velocity. So what is velocity? Velocity is defined as the rate of change of displacement. So if I have a car which is at the position x1 at the instant t1, after some time it displaces to position x2. Let's say the time at that instant is t2. So its displacement is given by x2 minus x1, which we can write as delta x, and the time interval needed for the displacement can be written as t2 minus t1 or delta t. Therefore the average velocity which is defined as change in position per unit change in time, can be written as x2 minus x1 upon t2 minus t1, which can be written as delta x upon delta t. Let's take an exercise to understand these concepts. A car was initially at 30 meters from the observer at 2 pm. People pushed it to 100 meters away from the observer by 2:10 pm. Calculate the average velocity of the car. At this point, if you want to solve the problem on your own, do solve it, come back and check the solution. Here goes the solution. x1 is equal to 30 meter, t1 is equal to 2 pm, x2 is 100 meter, t2 is 2:10 pm. Therefore, delta x is equal to x2 minus x1, which is 100 minus 30, which is 70 meter. Delta t is t2 minus t1, which is 10 minutes or 600 seconds. So what will be the average velocity? Average velocity is equal to delta x by delta t, which is 70 by 600, which comes out to be 0.117 meter per second. Let's see one more exercise to understand the concepts better. Please watch this video carefully before we go ahead.
Oh, they're away, and Gatling got away brilliantly, and he's ahead of the field at the moment, and Bolt going very, and here comes Usain Bolt! Usain Bolt storming through, he takes it again, Blake gets the silver, 9.64!
Now let's read the problem. In the video, Usain Bolt completed his 100-meter sprint in 2012 London Olympic Games in 9.64 seconds. After seeing the video, answer carefully the following questions. Was his velocity constant throughout? What was his average velocity during 100-meter run? Try to solve it on your own, then come back and check the solution. Here goes the solution. If you have observed the video very carefully, you will realize that his velocity does not remain constant. It increases initially, reaches a maximum, and it drops a bit towards the end. What will be his average velocity? So the distance he travels is 100, and you saw the time it took was 9.64 seconds. So the velocity will be 10.4 meter per second. So let's go ahead. It is right time to understand the position time graph. What is a position time graph? In a position time graph, we plot time on x-axis as an independent variable and position on the y-axis as a dependent variable. Here position is a function of time. For every particle we can draw a position time graph. One of the simplest position time graph is a line which is horizontal, that is parallel to time axis. Such a line represents a particle which is stationary or at rest, which is not moving at all. For example, if I have drawn this line as x is equal to 2 meter, it means the particle is stationary, lying at x is equal to 2 at all the time. Let's take another kind of position time graph. It's a straight line graph with a slope. Here you can see that the x position is changing with respect to time. In time delta t, if the position changes by the amount delta x, then the slope of the line can be defined as delta x upon delta t. But delta x upon delta t, as we have already seen, is also the average velocity. What does it mean? It means that the slope of the line in the position time graph gives me the velocity of the particle. What will happen if the position time graph is not a straight line, but instead it's a curve? So if it's a curve, then the ratio delta x by delta t will give me only the average velocity between the 2 points. We have seen in the derivative video that if you want the instantaneous velocity, that means if you want instantaneous slope, then in that case we have to shrink the limit of delta t to 0. So v instantaneous will be equal to limit of delta t tending to 0, delta x by delta t. But Again, we have seen in the derivative video that this is nothing but derivative of x with respect to t, which we can simply write as v. Therefore, velocity is a derivative of position with respect to time. Let's take an exercise to understand the concepts. Position of a particle varies as with time as follows. X is equal to 4t square plus 3t plus 1. Calculate its position at 1 second and 3 seconds. Calculate its average velocity in that interval. Find instantaneous velocity at t equal to 1 second by taking delta t as 0.1, 0.01 second. Take derivative of the equation and find instantaneous velocity at t equal to 1 second. So if you want to solve the problem on your own, please solve it, come back and check the solution. Here goes the solution. In A part, we have to find the position at 1 second and 3 seconds. That's very straightforward. In place of t, you substitute 1 and then 3 and get your answers. So x1 at 1 second will be 8 meter. x2 at 3 seconds will be 46 meter. B part, calculate its average velocity in that interval. So now we know the x interval, it is 46 minus 8, that is 38 meter, and we also know the delta t, which is 3 minus 1, which is 2. So the average velocity is delta x by delta t, which is 38 upon 3 minus 1, which is 19 meter per second. In C part, we have to find the instantaneous velocity at t is equal to 1 second by taking delta t as 0.1 and 0.01 seconds. In A part, we have already found the position at 1 second, which is 8 meter. In x2, we can substitute and find the position at 1 plus 0.1 second. So if you solve that, you will get it as 9.14 meter. Therefore, the average velocity in this interval will be 9.14 minus 8 upon 1.1 minus 1, which when you solve, you will get at 11.4 meter per second. Now shrinking the interval further to 0.01, what do we get? We get x2 as 8.11 meter. So what will be the average velocity now? It will be 11 meter per second. For D part, you have to take the derivative of the equation and find the velocity at t equal to 1 second. Derivative will be 8t plus 3. If you substitute 1 in place of t, then your answer will be 11 meter per second. So you can see that as the time interval delta t shrinks further and further to 0, your average velocity approaches to instantaneous velocity. Let's have a closer look at position time graph. Here we have curve whose slope is varying continuously. In the beginning, at point 1, it has a positive slope that shows that the velocity is in the positive direction. At point number 2, one can see that the line becomes steeper. As the line becomes steeper, the slope increases. That means the velocity increases at point number 2. At point number 3, you can see that the line becomes momentarily horizontal. That makes its slope 0, and therefore the particle is at rest at that point. As we go further, you can see that the x coordinate starts decreasing. That means the slope becomes negative. That represents the direction of velocity has reversed. At point number 5, again the line becomes horizontal, and that means the particle is at rest. Let's take one more problem to understand these concepts. In the following position time graph, find the velocity of the particle at different intervals. You can try solving this problem on your own, then come back and check the solution. Here goes the solution. Velocity is the slope of the curve at different intervals. Look at the graph carefully. There are 4 intervals from 0 to 2 seconds, 2 to 3 seconds, 3 to 4 seconds, and 4 to 5 seconds. So in the first interval, delta x will be 15 minus 0, while delta t will be 2 minus 0. So the slope is 7.5 meter per second, which is the velocity. It is positive slope. That means the particle is moving towards the positive x-axis. In the second part, you can see the slope is 20 minus 15 upon 3 minus 2, which is 5. The slope decreases. That means the velocity decreases. In the third part, the line becomes horizontal. For a horizontal line, we have seen the slope is 0, you don't have to calculate, and therefore the particle is at rest. Then for the fourth segment, the slope is given by 0 minus 20 upon 5 minus 0, which is minus 20 meter per second. It represents that the velocity direction has reversed. Particle is now returning towards the origin. So what is speed? In our day-to-day life, we talk about speed quite a bit. Instantaneous speed is nothing but the magnitude of instantaneous velocity. While the magnitude of the instantaneous velocity gives you the instantaneous speed, the magnitude of the average velocity does not give you the average speed. So be careful. Average speed can be defined as total distance upon total time. Speed is a scalar quantity. Remember, velocity is a vector. Let's take an exercise to understand the concept. A car travels the first half of a distance between two places at a speed of v1 and the second half of the distance at v2. Find the average speed of the car for the whole journey. You can try solving this problem on your own and come back and check the solution. Here goes the solution. Let the displacement in each half be x. Time taken to cover the first half. Since the speed is distance upon time, we can write time as distance upon speed. So t1 is x by v1. For the second half, it will be t2, which is equal to x by v2. The total distance, x in each half, the total is 2x. Total time is t1 plus t2, which is x upon v1 plus x upon v2. Therefore, average speed is total distance upon total time. So total distance is 2x, total time we have already obtained. So we can find the average speed, which when you solve, you will get as 2v1 v2 upon v1 plus v2. Okay, moving further from speed, what information we can get if we have velocity time graph? So from velocity time graph, we can find displacement very easily. Let's see how. Velocity is a derivative of position. So v is dx by dt. We can write x2 minus x1 is integration of v dt from the limits 1 to 2, which is nothing but the area under the vt curve between the limits 1 and 2. That means if you have velocity time graph in the form of a curve, then the area between the curve and the time axis within the limits 1 and 2 can be written as integration of v dt from 1 and 2, which is nothing but x2 minus x1, that is change in position or displacement. Therefore, if velocity is known as a function of time, then its integration with respect to time gives us the displacement. Let's take an exercise to understand this with clarity. In the following velocity time graph, find the displacement of the particle. Try solving it on your own and then come back and check the solution. Here is the solution. We have just discussed that in velocity time graph, area between the curve and the time axis within the two limits give me the displacement. Here this area can be divided into a triangular component and in a rectangular component. Therefore, the displacement delta x will be the sum of the two areas, that is the area of the triangle plus the area of the rectangle. The area of the triangle is half into base into height. The base is 4 second. The height is 2.5 minus 1, which is 1.5 meter per second. Therefore, it is 1 by 2 into 4 second into 1.5 meter per second. The length of the rectangle is 4 second. Its breadth is 1 meter per second. So if you multiply the two, your final answer will be 7 meter. So you saw it's a very simple way to find out the displacement. If velocity time graph is given, then all you need to do is simply find the area beneath the curve, and that area will give you the displacement. Here are some of the review problems given to you. Please go through them. They will help you to understand the concepts better. In this video, I am giving you a project. This project is based on the video that we have seen in one of the examples. The data has been given to you. If you can do this project completely, you can mail it to me. The email address is provided, physicsin20minutes@gmail.com. Here are the activity problems given to you. Please solve them. Here are the answers to the activity problems. Thank you.